All right. Welcome back, everyone. Let's get started. Today we're gonna be exploring LeetCode's weekly 362. Maybe you have participated in it yesterday, or maybe you didn't. Hello, Lucia. Welcome. In any case, I'll try to say as many interesting things about the problems as I can so that everyone can learn something. So let's get started. Let me share first the link of the contest. I'm gonna pin it. And then let's get started with problem 1. Points that intersect with cars. You're given a 2D integer array nums representing the coordinates of the cars parking on a number line. For any index I, nums of I is start I and end I sub I, where start sub I is the starting point of the ith car and end of sub I is the ending point of the ith car. Return the number of integer points on the line that are covered with any part of a car. Okay, so we're given intervals that represent the endpoints of cars, and we essentially need to return the size of the union of these intervals. So here, for example, in example 1, we have this car. So cars can intersect. So it's weird that the intersect. Oh, yeah, I guess you can think of the whole thing as one interval, and you want the intersection between that and all the cars. Because I think of this as the union. In any case, so in this case, all the points from 1 to 7 inclusive are covered by the cars intervals. So there are 7 points that are covered. And so, yeah, so this is an easy problem. So let's try to find an easy solution. So the constraint, first we check the constraints. There are only 100 cars or intervals, and the range of the values is within 1 and 100 inclusive. So that means that we can do something brute. So we could go over all the intervals and go over all the points inside of the interval and marked as covered. And then we covered them in some kind of data structure that has all the range, and then we count how many they're covered there. So in that case, if there's a point that is covered more than once, we just mark it every time, but at the end we're gonna have it marked or not, and we count it only in that case. So that should be an easy way to solve this. So how do we do this? So we're gonna say covered, whether it is covered or not. And we're going to create an array. And let's just use a constant. Why not? So this is going to have point for 0, which is not in the range, but it doesn't matter. We're going to leave it there. It won't be covered, so we won't count it in the end. And then for 1, 2, 3, and so on, up to 100 inclusive. And so then we go over all the intervals, and for x in the range start, and we want n to be inclusive, so we add 1. So we say that this point is covered. And finally, we want to add all the covered. So we can just do this in Python, and it should work. And we got the examples right. Is there an edge case? I don't think so. So let's try to submit it, and we got accepted. So this is good enough. Here, I guess instead of using the maximum, we could so the a constant, we could choose the biggest end. So for this, and we need to add 1 so that we include that end. And this should save memory for smaller cases, and we get accepted again. Let me share this solution. So what happens if the sizes, so what happens is the range, so even if we have, so what's the order of complexity of this? This is, so we go over 100, in the worst case 100 intervals, and then for each we go over all the points inside that could be 100. So that means it's 100 by 100, which is 10 to the 4, which is 10,000. So that's not much for LeetCode's, so that's why this works. However, what if the range was big? Let's say that we still have 100 intervals, but what if the range was, so this was 10 to the 9 or 10 to the 18 even. So in that case, we cannot go over all the points in each interval. So how do we do this faster in that case? Well, so there is a trick, a technique for going over a union of intervals without all going inside of all the included points on each interval, just going through the endpoints of the intervals. And so yeah, maybe I should draw something to explain this. So let's say we have an interval here. So this is start and end, and this is I. Then we have another one, and this is start of I plus 1 and end of I plus 1. So what if instead of storing the intervals as pairs, we store the endpoints independently? So we store this thing and this thing and this thing and so on. we store them independently, and we're gonna remember whether they are a start end or an end end. Okay, so in that case, if we sort them, if we sort all, let's call these events. So events are whether an interval starts or an interval ends. So then we can sort them by their position, and we can go over them in sorted order, and we can keep track of how many. So essentially we are kind of breaking this down into segments where we have at least one event, and since there are only 2n events, this is going to be linear in the number of intervals, and within 2 events we can check how many intervals there are covering that segment, covering that distance between 2 events. And if there's more than one, then it means that it's covered, and if there is more than 0, it means that it's covered, and if it's 0, it means that it's not covered. So that is what we can do to make this fast. So that would be linear in the number of intervals. So that means that this could be, for example, 10 to the 5 or more. So 10 to the 5, and this could be numbers up to 10 to the 18 that can be stored in a 64-bit number, and it would work. So let's try that. So again, we're gonna go over start and end in nums, and we're gonna store the intervals as events. So events, I'm gonna append a pair start with a 1, which means that we are adding 1. We are opening an interval, so we are adding 1 to the total number of intervals. And here we're gonna append the end, but so this start and ends are both inclusive, but oftentimes it's more convenient to represent intervals as closed and open, as inclusive and exclusive. So this would be more convenient to use end plus 1 so that the end is not inclusive, it's exclusive. And minus 1 because we are closing one interval, so the number of intervals will be reduced by 1. So now we sort them, and now we won't. So we go over them. Okay, so this is the current position, and this is the, so we're gonna have a previous position with a number that is less than all of them, or it could be 0 because 0 is not included. And then we're gonna call this the delta, which means it's the change in the number of and this is going to be the number or the count of intervals that are open. And so we want to know if the segment, so we have an event between current and prev. Okay, so these are two consecutive events. So we want to know if the current count is greater than 0, because if that's the case, then we are covering this distance between consecutive events, so we're going to add it to the result. And then we want to update the count with delta. So that means that if this is an open event, it's going to add 1, and if it's a closed event, it's going to subtract 1. And we want to update the prev with current. And finally, we return the count. So we get this, and it's accepted. All right. So this one took 71 milliseconds. So this is not a big, I mean, it's the same, but the reason is because the input is too small to make a difference. But if you had bigger numbers, then you would see a huge difference. I mean, one would not end practically, and the other one would. And so I don't know if it was clear why, hey, Lucia, I don't know if it was clear why it was more convenient to use n+1. So this is the current position, and there's a previous prev position, and we have the yes, that's true. So yeah, it's a little tricky. I don't want to dive into it. I think you can do it in both ways, but notice that since we are sorting pairs by their values from from in increasing order or non-decreasing. So if we have ties of events, all the -1s, the ones that are closing, will come before the +1s. But in any case, if you have things that are have the same position, then the length of the interval is going to be 0, so that's not going to add anything. And that means that when we look back, we are not considering the current. We are considering all the positions from prev up to the previous one of current. And that is what our count is counting. So that's why we check if count is 0. In that case, we don't add it. And if it's greater than 0, then we do. So yeah, maybe you have to think about it a little bit. But if you, this is a very common algorithm technique for dealing with intervals and doing something with the union, or so decomposing it so that you know how many there are, covering every segment or every subsegment. So I recommend you to study this technique. So let's move on to the next one. Did I share? No, I did not share the second solution. Let me share it. So it's not, yes, it is this. It's submission. Cool. So if you have any questions, you can make them in the Twitch live, and I will try to, if you have questions about things that are not clear, I can try to answer them. And if you're watching this afterwards, you can add questions in the comments of YouTube, for example. Because sometimes it's hard for me to know what the misconception or what's not clear about, for example, this decision of using n+1. But if I have a concrete question, it's easier to try to clarify why we did that. Okay. Anyway, so let's go to the second question. Determine if a cell is reachable at a given time. You're given 4 integers, s of x, s of y, f of x, and fy, and a non-negative integer t. So you start at the start. This is the start coordinates, and you must move to any of its adjacent cells. And adjacent cells means any of the 8 cells around it. So diagonals are considered adjacent in this problem. And we have to return true if and only if f of fx and fy, so the final position can be reached after exactly t seconds. All right, so we get 2 examples with some nice little drawings. And here you can, because this distance is 6. Well, it's 7. There are 7 squares, but the distance is 6. So it's good. And here you cannot. Because, so you have time 3, you have 3 moves, and you need at least 4 to get there, so you can't be there so quickly. And then the numbers are big, up to 10 to the 9, and the time can be up to 10 to the 9 as well. All right, so what do we do here? What do we do? So, well, a few observations. First, if you like chess, you might notice that this is how kings move. So kings can in one move to 8 of the squares. So maybe you can use your intuition, your chess intuition for this problem. So, lol, what are you laughing at? Sorry, I missed that. Anyway, so yes, this is king distance. So maybe you haven't thought about this, but how do you compute the minimum distance between 2 squares? The minimum number of the minimum number of king moves to get from one point to the other. So that's not exactly this problem, but it sounds interesting and it sounds relevant. So let's think about it. So let's say that we have to move. So let's say to simplify that we are here, we're at the, this is without loss of generality because we can move things, we can translate things, and let's say that move here, right? So it's pretty clear. So let's call this x and this y. So it's pretty clear here in the drawing that this side is much longer than this side, the x side. So you can always move. So you'll have to move. So let's call this the x, and this is the y. So you obviously have to move at least the y or the x. Otherwise you cannot move. You can think of this as moving independently on each dimension. So if we move less than the x, you're not going to get to the end. However, so that is necessary, but is it sufficient to move the x? Well, the answer is yes, because when you move diagonally, you're moving one in both directions. So you can try to do a shortcut here and move you move both directions, and you're gonna reach this, the I coordinate, before reaching the x coordinate, because dy is less than x, and then you move this way. So that means that you had to move x, you have to make x move to get there, right? So this is x and y. And that means that our distance is the maximum of dx and dy. This is the minimum distance to get from 0, 0 to x and y. And what are dx? So dx is the distance in one dimension and the other. So if you are not in the origin initially, dx is going to be x1, if we call this, and x2. And so this is the distance, which is the absolute value. And this is y, sorry. This is y1 minus y2. Cool, so now we know how to compute the minimum distance between 2 points in the grid or in the plane. But this is not exactly our problem, right? Because they are asking if, so the number of moves is fixed. We have to make exactly t moves. So forget about the time. You can think about it in terms of number of moves. So we have to move exactly t times. Can we finish at finish? So how do we know? So obviously, if the number of moves that we need to make is less than the minimum that we need to reach it, then that's obviously, that means that we cannot, right? So if the number of moves, which is t, is less than the minimum, which is this, then we cannot. So we return false. And what happens? What if t, so now t is greater than the minimum. Don't be confused by using the maximum. So this is the minimum distance, which is the maximum of the two. So notice the distinction between minimum here and maximum here. The minimum distance is the maximum distance on each dimension. Anyways, so how do we, so is it, so that means that it's necessary to do, to have at least minimum steps. But is it sufficient? If we have spare moves, can we always do it? And the answer is complicated. So let's try to think about it. So you have So if you have exactly mean moves, then obviously you can, because you do this path and you get there. But what if you have more? What if you have spare moves? And so let's think about a strategy. So what if we move? So if you move in a shortest path to the finish position, so every step reduces the minimum distance by 1, right? So at one point you're going to be in an adjacent square, or distance 1 to the finish. So let's say that this is the grid and this is our destination. So if we have spare moves, at one point we're gonna get, so this is not good anyways, at one point we're gonna get to one of these squares, of the white squares around the finish line, and then we can start moving around it, right? If we have spare moves, we can start moving around it. So we move here, we move here, from here to here, and so on, and we can move as many times as we want. And when we have only one move left, well, then we move to the finish line, to the finish position, square, and we're done. So that seems like we can always do this, right? So should we return true if that's the case? Well, there is something that I said which is not always true. So I said that when we move from the minimum path, through a minimum path from the start to the finish, at one point we're going to be at distance 1. But there's an exception. So what if we are initially, the distance is 0? If the start and the finish are the same point? Well, in that case, we're going to be at distance 0. And what happens there? So if we have spare moves, we need to go out. So again, we're going to be so this is the start and the end in this example. So we first move away to any of this, and then we can apply our strategy of going around. We go around, we go around, we go around, and then we move back, right? So we move here, here, whatever we like, and then we go back, and we did it. But that is assuming that we have more than one move, right? Because what happens if we have only one move? We move out and then we're done and we're away from it. So that is an edge case where we cannot do it. If we have only one move and we are already in the finish, we cannot do it. If we have more, then we can apply this strategy and we can do it. So that is a very tricky edge case that to be honest, I'm not gonna lie, I missed and I got a wrong answer, and then I realized. So how do we write all this? So let's say I miss it too. Yeah, no worries. So yeah, I think that trying to prove it like we did helped us identify our assumption and realize that there was an assumption that wasn't always true. So here we said that the distance is the absolute between the differences and sy minus fy. So this is the min dist. Okay, so we want the min dist to be greater than or equal to t, and we don't want the edge case, which is min dist 0 and t1. No, this is the other way. So t has to be greater than or equal to the minimum distance. Yep. Accepted. All right. So yeah. So this is a tricky edge case. But like I said, if you try to prove your algorithm, you're able to, you can catch it, maybe. And remember, so that strategy of going around was interesting. There might be other strategies you can go. So so you don't have to do the whole round thing, right? You could move between two positions, right? Back and forth. The important thing is to stay at distance 1 from the finish. And if you go through the finish, then you're not at distance 1, you're at distance 0. So this is all I have. So I shared my submission. Good. So let's do this one. So I have a lot of things to say about each of them, so bear with me. I think you're gonna learn a lot. Minimum moves to spread stones over a grid. You're given a 0 index to the integer matrix, and representing the number of stones in each cell. The grid contains exactly 9 stones, and there can be multiple stones in a single cell. In one move, you can move a single stone from its current cell to any other cell if the two cells share a side. Return the minimum number of moves required to place one stone in each cell. All right, so here we see examples. We have nice drawings. Thank you to LeetCode. Well, so the size is always exactly 9. It's always 3 by 3, and you have exactly a total of 9 stones. So the sum of the numbers is 9. So on average, you have 1 per cell, but you will have accumulations. So you're going to have cells with more than 1, the average, and cells with 0, with less than 1. And so notice that you will have the same. So here you have 2 extra, and here you have 2 extra. So you have 4 extra stones, and you have 4 zeros. That's always going to be the case, of course. Here you have 1 extra and 1 missing. And so here it's pretty obvious that you need to move from here to here. There's only one minimum path, or I mean 1 minimum length. It's 3 moves, and that's why this is 3. And so, but here is not as clear, right? Because where do you move? Here there are 2 extras, here there are 2 extras. What's the best? So here, I guess this is kind of a matching problem. You need to decide where you move each stone. But when you move a stone from here to here, for example, then this extra stone cannot move here because now it's occupied by a stone that came from here. So there's some dependencies between what you do. That's why it's not as clear what's the optimal thing to do. In this case, it seems simple because there are two for each. There are two that are adjacent, and the others are at distance 2 from the extra stone. So it's pretty easy that you want to prefer the two closest for this and the two closest for this, and there's no conflict. But sometimes there could be one place with 0 stones that is at the same distance from extra stones. So which one should you choose? It depends on other things, on whether there is another close slot to one of them. That's how you would decide. So you should realize that this is not very easy to know exactly where you should move every stone. So with that in mind, this is called a bipartite matching. I don't want to dive deep into it, but so if you count the multiplicity, the extra stones, so here there are 4, and here, so there are 2 here and 2 here, there are 4, and there are 4 places to put them. So you want to match four things to 4 things, so that's why it's bipartite. But anyway, forget about that. Let's see if we can do something. So whenever you realize that doing the optimal thing is not very easy, so you don't find like a greedy choice, you should first think about doing something brute. Okay, like trying all the possibilities. So it seems like this is pretty small. There are only 9. So this is 3 by 3 always, and there are only 9 stones. So this is small enough. So maybe we can do something going like trying to make one move at a time and trying all the moves and seeing if we found eventually we find the final configuration. We has 1 on each. So maybe we can do something like that. So how do we know if we can do that? Well, maybe we can count how many configurations there are of this thing, right? So, because it doesn't seem like, again, intuitively, there doesn't seem to be many. For example, if you think about that there could be on each position, there could be from 0 to 9 inclusive. So that means there are 10 possibilities for each. And there are 9, so 10 to the 9 is not a huge number. It's not tractable in LeetCode, but it's tractable. Maybe in 1 minute you can run a program that goes over 10 to the 9 states. But this is a very it's not a tight bound, because I'm assuming that I can put any number here and then again any number, but they had to add 9. So how do we count exactly how many there are? Well, there are a few ways to do that. So one way is to just write a program. So maybe we can write a quick program that counts how many. So we have 9, and the sum has to be, it's 9 initially, and we have we have to put a number of stones in the first place up to 9. So so if we haven't gone over all of them, we can put between 0 and the minimum between 9 and s inclusive. Those are how many stones we can put in the current position. And we go to the next one and we subtract how many we put them, and we add up everything. And if we have put all the stones, we need to make sure that there are 0 left. And we can cache this, and we call it, and we print it. And this should tell us how many configurations, which is 24,000. Okay, so don't so this is a valid strategy. Maybe sometimes you don't think about that. So this is why I said this is think like a pro, because maybe sometimes it's hard to realize that you have these resources available, that you can write a program to count it. Maybe you think you must do find some formula, but we are programmers, so we can program. But there's another way to count this, a more mathematical way. So we want to distribute 9 things in 9 places. And there's a famous mathematical problem which is called, so let's say the things that we need to distribute are called stars. And these are bars. So maybe you have heard about the stars and bars problem. So the bars are so they're not exactly 9. There should be 9 minus 1, because we have 9 slots, which are the places in the grid. But we can think about the divisions between slots, and there will be 8 divisions. So for example, if we have only 1 division, that means that we can put something here and something here. So notice that any permutation of any combination of these things of 9 stars and 8 bars will give us a solution, configuration of the grid. So for example, if we have something like this, so maybe I'm not gonna draw them all, but this would mean, so here, if we translate this into a grid, so well, it doesn't have 8, so it has 6. So let's say there are more here. So there are 5, there's 7. So now I have 8 bars, which is what I want, and when I have 5, so let's put a few more stars here and 1 here. So how does this translate to a grid? Well, in the first one we have 3, in the second one we have 0, in the third one we have 3, then we have 0, 0, 0. So I'm counting what's between bars, and here we have 1, 1, and 1. So it adds up to 9, and we have 9 places. So there's a bijection between this and this. So if we count this, we count this. So how do we count this? Well, we have 9 plus 9 minus 1 slots in here where we can put a star or a bar. And we need to choose 9 of them, which are the slots that will have a star, and the rest are going to have bars. So that means that this plus this minus 1 is 17. So this is the number of ways to choose 9 things out of 17, and that's going to be our number, which if we go and calculate it, so choose 17, 9 is 24,310. Which is exactly the number that we've got here. All right, so there are many ways to do things. Nice, yes. All right, so now we know that there are only 24,000 combinations or configurations. So maybe we can move over all of them, but we have an initial one, and we want to move to a final one which has all ones, and at each point we want to change one to move one of the stones, and that's considered one move. So this is a graph that is unweighted and that has 24,000 nodes. What do we do to find the shortest path in a graph from one point to another? We use, and it is unweighted, we use BFS, breadth first search. So this is a BFS problem, all right? However, the nodes are a little tricky, a little complicated, because they are represented by these grids of 3 by 3. So how are we going to represent them in the code? I'm glad that you asked. So this is the representation that we get, right? A list of lists of ints. And that's fine. The problem in Python is that for BFS, we need to mark nodes as visited. And we use a set to mark nodes, to add them to a set, so that then we can ask quickly whether we've seen them or not. But we cannot use lists as as elements in a set, because they are mutable, and mutable things are not hashable in Python. So, but we can transform them, we can translate them into tuples, which are immutable or are hashable. So we're gonna do that. So we are going to have two helper functions. One that receives a grid in the problem format, and it's going to yeah, I don't think we need to. So this is a row for row in grid, and we want to convert the row into a list, and we return a list of that, and that's it. So we turned the list of lists into a tuple of tuples, and then from tuple we want to go over the row in the grid. And we want to transform this into a tuple. Oh no, so this is, I'm getting this, so I'm distracted. So this is a list, so I turn it into a tuple and I turn this into a tuple, right? And then I get a tuple, I turn it into a list and a list, that's right. So yeah. So don't worry, I make them mistakes. You can't be a pro and make them mistakes. That's my whole point. The key in life is not to avoid making mistakes, but to don't dwell on them and correct them as quickly as you can. So here we are. So we have the starting position, which is this to tuple, and then the finish position, which is all ones. So maybe we can have a constant here. I prefer to use constants if I can. And so. So let's make it because I don't think we can do the multiplication for tuples like we do here. So that's why I prefer to make a list and then transform it to a tuple. And so we have so the usual BFS, we use a queue. We put the start first, the start node, and we have a scene set with the start node as well. And we have to return the distance, and we always can. So while the queue is not empty, which is never going to be, so yes, one way of doing DFS is with two loops. So here we go over, so we go in order from level, and this is U, the current node. Let's call it U. So we pop left, and if U is equal to finish, then we found the finish node. And otherwise we want to move, to make a move, right? So how do we make a move? Well, we go over all the positions in the grid, and if we found a position that is greater than 1, which means that it has extra stones, then we want to move it. So where we have 4 positions potentially to move it. So this is how we go to all the adjacent positions, the 4 adjacent positions in a grid. Well, so no, this is 0, 1 and minus 1, 0. So yes, these are all the possibilities. So then this gives us the next positions, and we want to check if they are within the bounds. and we want to create the new tuple, the new node. How do we do that? Well, so there are a few ways to do this. We can make a from tuple of u, and then we know that this has one extra stone, so we subtract it, and then this is going to receive an extra stone. And now we want to turn it into a tuple so that we can insert it. And if b is not in scene, then we add it and we append it to the queue. Three, 4, and accepted. Cool. So I wanted to teach another trick to do this, because I feel that this kind of representation is a little clumsy. So there are more compact ways of representing this information without so many tuples of tuples and lists of lists. So let's do another one that uses a, so yeah, maybe let's remove this so it is not added. So yeah, let me first share this solution, which is good enough. The time is 2 seconds. I don't know if this is significant here. I hope not. It shouldn't be significant. Just wondering, are you solving this problem live for the first time? No, I don't wanna give you that impression. I solved them today, but in order to give this many insights into alternative solutions and alternative ways of looking at it, I had to prepare a little bit. So, but in any case, I try to remember my thought process while I was solving them for the first time, and I try to explain it from that point of view. So I hope that answered your question. Yeah, great. That's great. Yeah. So I do some strings in which I read the problems for the first time. So check them out. I'll be doing more. I think I did one yesterday. I think I usually call them improv or something like that. So yeah, check them out if you are interested. Anyway, so yeah, so I wanted to quickly do some code. So hey, thanks for the follow. Thank you. So I wanted to do, so there's another way to represent this in a more compact way, and that is with bit masks. So don't be afraid of them. So bits are a cool way of encoding information in computers. Backtracking. Yeah. That's good. Yeah, I think there are many ways. So is it really backtracking what you're doing, or is it more of are you memoizing anything? anyways, so instead of having this to tuple and from tuple, let's have an encode for a grid. So I'm not gonna dive into the details. Maybe you can, well, if you make a question, I can answer it, but otherwise it might take too long to explain it. So we want to encode a grid as a number, and so the grid is essentially a list of 9 numbers. So yeah, first of all, the grid is 2-dimensional, right? It's 3 by 3. So let's have something to get an index. So let's turn it into a 1-dimensional. So if we have row and col, then, and we want to have one number, so then we can multiply the rows by 3 and add the columns, and that's going to give us a number, an index between 0 and 8 inclusive. And then we can have the opposite. So from index, well, I don't think if we know. Let's keep it this way. So anyway, so here we want to go over. We want to go over the grid, and we want to encode it in a number. So here, the value that we're interested in is this, and the index for this position, it's I here, and we're going to be using, so the numbers that we want to add to the integer or encode are from 0 to 9 inclusive. So that means that we need 4 bits to encode them, right? Because with 3 bits, we only have 2 to the 3, which is 8 possible values, but we need 10 values. So that's why we need 4 bits. So we want to move this 4 bits well, let me do this more clearly. So for every position we're going to use 4 bits. So that is how many times we want to shift it, and this then OR it with the result. So that's going to give us the code of a grid. And then once we have the codes, we want to be able to get a value from the code. And how do we do that? Well, again, we get the index for the position. And then we do the same that we do usually with bit masks, which is that we shift it, but this time is we have to multiply the index by 4 because we use 4 bytes for each position. And then we want to AND it so that we only get the last 4 bits with 15, which is 2 to the 4 minus 1. So 2 to the 4 is 16 minus 1. So this is going to give us the value in the ith position of the code. So let's start translating this. So this is going to be encode. This is going to be encode. Here we want to get from the code U the R and C value. All right. And now we're gonna need these operations, right? We want to add one or subtract one to a position. So let's do that. And here we're gonna have a delta of how much we want to add or subtract. And again, we get the index, and we are going to return from the code. We're gonna add, again, we want this 4 times. So yes, we want this 4 times, and we want to shift delta this many times and add it to the code. So, and that's going to give us a copy. So we want to add from the code U, position R and C -1, and then this is going to give us a code, and we want to add to that code positions R and C to 1, and this is going to give us B, and that is it. N is not defined. We don't have N anymore because it's a little more complicated. No, well, it doesn't matter, but yeah, we could have N. I don't know why I changed it. Generator is not subscriptable. So this is, oh yeah, I think this is the problem. Again, another N, line 40. And here, and here. So we get the right answers and accepted. And is it faster? Maybe not. So this took 2 seconds and this took 1.5 seconds. So it is faster. Let me share it. Cool. So let's get to the last one. All right, so string transformation. So this one is a tricky one. There was only 97 accepted. So I solved it in a way that I don't know if it's the simplest solution, but it's the one that I could think of. So I'm gonna explain that one. If you find a better one, let me know. I'm interested. So I did not dig into other solutions from other people. Maybe I should have. But usually I have fun by thinking about the problems on my own. Maybe start looking for Googling some subjects and techniques, but I don't want to get spoilers for the problem itself. So I apologize if I'm not giving the best solution or better solutions that I could find. I'm sorry. Anyways, so you're given 2 strings S and T of equal length n, and you can perform the following operation on the string s. You can remove a suffix of s of length L, which is within and excluding 0 and end, and append it at the start of s. So we get an example here. You remove the suffix cd and you put it at the beginning, and you get cdab. You're also given an integer k. Return the number of ways in which s can be transformed into t in exactly k operations, and modulus or so and so as usual. And the strings can be pretty long, 500,000, and k is very big, 10 to the 15, sorry. So all right, so let's write down the mod, which otherwise I will forget. All right, so how do we do this? What do we need to do? How do we understand this problem? So, well, the first observation is that, so let's try to understand this operation, all right? I think that's the first step. Try to understand. This is usually, try to find more intuition or a different representation for things is a good way to make progress. So notice that when we remove a suffix and we add it as a prefix, you can think of that as a rotation, right? So you can do this. So in this case, you're removing CD. Notice that you can do it by first removing the D and putting the D here, and then removing the C and putting the C here. So we are what is called rotating. So we can think about this in other terms. Instead of changing the string, we can think of having one position, the starting position, if you will, in a circular array, right? So here we're at position A, and we jump to position C. And that means that now we start from C to D and we wrap around because it's circular, and we're at A and B, then it's A and B. So that's another way to represent these changes. Instead of changing the string, we keep track of the first element in a circular array. And then this becomes jumping, right? So the only catch is that when we jump, we have to jump one place. The minimum jump is one place. We cannot stay at the same place, and up to n-1, right? Because otherwise we would, again, not change. So with this representation, this problem becomes we have to do exactly k jumps, and then can we land in a place where the strings match? So that's one thing, that's one observation. We understood better what the operation means. But now we said, well, we want to know if we end up in a position that matches, where S matches T, for starting from our current position. So the matching, that's a matching problem. It's a matching problem of strings, right? So how do we know? So we could try to find out for every position whether starting from there on S, on a circular array, whether that string matches T. But if we do that naively, it would be quadratic, right? Because we have to start at each letter, each position from S, and then go over T, move in both, wrapping around on S, and checking that all match. So we could do that, and we would find out all the positions that are matching, but it would be too slow. And there is a very well-known algorithm for doing this quickly. Instead of doing it quadratically, we can do it linearly, and it is called KMP, which means Knuth Morris Pratt, which are famous computer scientists. So we can solve that problem. That problem is important for solving this. It's not all that we have to do. So I'm not gonna dive into the explanation of KMP. I'm gonna use it as a black box. I might do another stream explaining it. But sometimes it is useful to know algorithms as black boxes. So understanding what the interface is, what the input should be, and what the output will be, and what the order of complexity is, and so on. But so I'm gonna be copy pasting it here. So this is an internal helper function. We are not going to dive into that. And this is the function that we want to use. And this is going to get a big string and a smaller string that we want to search in S. We want to find all the matching positions of W on S. And we are going to return, this is going to return the index where that match starts, okay? That's what the result is going to mean. So yeah, maybe I should write it here. Returns all the matching positions of W in S. Okay, so we only need that to use it. But since this is a circular array, instead of passing S, we're gonna pass 2 times S. So it wraps around. So that we don't have to wrap around and we can reuse. I use this trick in another problem. So we want not exactly 2 times. We don't want to have it exactly 2 times, because otherwise, if W is this, if T is the same as S, then it's going to match it 2 times, but we want it match it only 1 time. So want to remove the last element, right? So find of this and T. And that's going to give us the matches, all the points where it matches. All right, so if there are no matches, then it doesn't matter what we do, where we land or anything. So there's going to be zero ways to end up matching, right? Let's see what this does. well, there is no case where there are no matches, but maybe we can add one. So what is the shortest length here? 2. So if we have AA and BB, then we should get 0, which we do. So that's working fine. Okay, so now we know what positions match. So now this becomes, so now we can forget about the strings, right? Because we even only want to know how many there are. So how many, let's say that Q is the number of matches. So let's say that we have, oh, my tablet turned off. Let me turn it on. All right. So let's say that we have, so we have the, we only have the position. We put the positions on S. So what we did was to mark some of them. So let's say that here, if we start from here, there is a match. And if we start from here, there is a match. And maybe if we start from here, there is also a match. Notice that matches wrap around. But if we start from here, there is no match. So we basically classified all the positions into matching or non-matching. And so what if we only cared on whether we are on matching positions or non-matching positions? So maybe we can represent this information as a graph, right? Where one position, so yeah, let's write it. So we have one node, which is the matching node. Let's call it 0. And we have another node, which is the non-matching positions. And so here, from one of the matchings, so notice, if we're here, we can move here, and vice versa, or we can move here. Those are the ways where we can move from a matching position into another position. Remember that we have to do jumps, right? So this edge is going to represent moving from a matching position to another matching position. And the same you can do here. So this is what's called an hypergraph when you accept loops. But that doesn't matter. I mean, it's just a graph with a directed graph with loops. So edges that go from one node to another. And then we can move from a matching position into a non-matching position, and from a non-matching to a matching position. So this kind of represents all the, so we partition the nodes into 2, and this represents all the movements that we can do. If we don't care about the exact positions, we only care about the class. So, and notice that this edge, it has some multiplicity, right? Because if we are, so let's say here that there are Q, green and n minus q red. So that means that if we are in a green position and we want to move to another green position, we cannot move to the same position. We have to move. So that means that there are q minus 1 ways to move from a green to a green. And there are n minus q minus 1 to move from a red to a red. And there are n minus q ways to move from a green to a red, because there are n minus q reds, and there are q ways to go from a red to a green. All right, so here we have a graph. So there's another way to represent this graph, which is with an adjacency matrix, right? So this is 0 to 0. We have q minus 1. And then 1 to 1, we have n minus q minus 1. And then 0 to 1 is n minus q. And then 1 to 0 is q. So this is the adjacency matrix of this graph. So let's rethink what we're asked to do. We are starting in position 0, which could be green or red. So we need to figure out whether we start in 0 or 1. And then we want to move k times in this graph, and we want to end up here in 0, which is a matching. We want to count how many ways there are to move k times in this graph and land in 0. All right? So there is this is a famous problem, which is counting the number of paths in a graph, which can be done by multiplying these matrices, these adjacency matrices. And hey guy, hey Creepypasto, how are you? So I'm trying to think if I want to, this is a little complicated, I think, to explain why the multiplication relates to the number of paths, to counting paths. Maybe we can use it as another black box, as we used KMP, but it has to do with the fact that, so if you remember matrix multiplication, so when you multiply, so let's say this is A and this is B, so this is just a 2 by 2 matrix, so like you see here, so it's not a big deal. But remember that you multiplied row with column, and so the resulting matrix it has to do with the fact that this is going to represent the number of paths from 0 to 0, and this is the number of paths from 1 to 0, and so on. And if we multiply by this n times, that's going to give us the number of paths of length n that between each of these nodes, okay? So this is going to boil down to compute the power of a matrix quickly, because here the exponent is a big number, right? It's this k, which is up to 10 to the 15. But we can't forget that this is a matrix for a moment, and we can say, so we want to compute a to the n. So there's a method to compute powers by squaring, which is of order logarithm, and it's based on this fact that, so this is the same as, so n can be written as, can be decomposed as 2 times q plus r, where r is it's 0 or 1, and so that means that this becomes 2 times q plus r, which, applying just the rules of exponents, it's the same as a squared to the q times a r. So remember that this is either a or 1, because r can be 0 or 1, and here q is it's n divided by 2, so that's why you are doing a recurrence by getting the half of the exponent. So with this idea is how you can do the power very quickly in logarithmic time. So I think that's all we need to code the solution. Okay, so we said that q is the number of green positions, and let's call n, this is big brain stuff. So let's create the matrix A, the matrix that we said right there, the one that we draw here, which is q minus 1, and then n minus q, and then let's just copy, why not, q and n minus q minus 1, n minus q minus 1. So let's so yes, in the diagonal we need to subtract 1 because we cannot go from one node to the same, so 1 is discarded. N minus q is the number of non-matching, and so yeah, in q is the one sort of matching, so this is correct. Then we want to do the power of a to k, and then we want to know whether we are starting, from a 0. So if the matches, the first match is at the beginning, at position 0, then that means that we are starting in a matching position, and that means that we call 0 the node for the matching positions. So we are starting at 0, otherwise we are starting at 1. And that's why, so finally, when we get the power, we want to count the number of paths from start of length k, from start to finish, and finish is always 0 because those are the matching positions. So this is it. But now we have to implement power, right? And this is based on very standard code, which is what I explained. It's based on the formula that I explained. So I'm not gonna dive into it. So we want to multiply res by a if it is odd, and then we want to multiply to do the square of a, and then we divide b by 2, and then here this is going to be the identity, which if you are using integers is going to be 1, but this is the neutral element of multiplication for matrices. And then we need to write to multiply two matrices, and we can do that easily in Python. So these are very small matrices, and then we go over. So this is standard matrix multiplication, but we want to do this mod. And that's it. All right, so we didn't get it right. How do we debug this? Let me first so let's read matches first. Oh no, so we okay, that was a dumb mistake. Oh, so we do get the right answers, it seems. That is always good. All right, let's try our luck. And accepted. That was easy peasy. Cool. So yeah, maybe this one is requires a few bits of knowledge to follow. Sorry if I did not dive into all the implementation details. I want to try to do a KMP stream once so that I have it in my YouTube channel collection. This one is very standard, but in this case we're multiplying matrices instead of numbers. Nice, it was hard. Yeah, I mean it requires, I mean they are well-known algorithms, but you have to figure them out and implement them quickly. I don't know, like I said before, I don't know if there's an easier solution that does not require. I think KMP should be inevitable, but well, sometimes this matrix multiplication thing, you can do sometimes some kind of DP instead of doing it this way, but I usually do it this way. But the code, I think, it's not a big deal if we pasted KMP, and then this helper functions are very standard. And there's not much code here, so I think the explanation was a lot longer than the code. The code came out pretty easily. So yeah, that's all I have. This has been 1 hour and 45 minutes. I think that's enough. I don't have anything else to say about this contest for now. If you have any suggestions, if you find better solutions, let me know in the comments. And if you have any corrections, I really encourage people to give feedback to me, so it's welcome. So yeah, that's all I have for today. Thanks a lot, guys and gals. See you in the next one. Bye bye.